Good morning, dear students. In today's video, we are going to see the detailed core architecture of ARM7. As we all know that ARM stands for Advanced RISC Machines. Now going into the details of ARM7 architecture, to be on a lighter side, this is the symbolic representation of Advanced RISC Machines in the year 1999. And now in the latest years, this is the symbolic representation of an ARM processor. And we all know that we have heard about Nokia 6110. That is the first ARM powered GSM phone. And we could all remember recalling, playing snake game by using this Nokia 6110. Now coming to the details of the ARM architecture. So this is the entire architecture diagram for you. Here you can see that these are the various parts that are available in an ARM architecture. We'll be seeing the details one by one. And the reason why this diagram is called as a data path design is because we're going to see how data would be traveling across all these blocks, and then what are the different paths that the data would be taking during fetch, decode and execute phase. Now coming to before we start with the architecture, let me just tell you that it has got ARM7 has got a 32-bit address bus. So hence it can access a total of 2 power 32, which is equal to 4 GB memory space. And we know that the memory in ARM7 is based on von Neumann model. So this memory space contains both program as well as data. Now coming to the next one, ARM7 processor also has a 32-bit data bus. This bus is used to fetch both instruction as well as data. And both the instructions and data that are fetched are 32-bit in size. Now coming to the register files, as you can see in the picture, this is a major portion of the ARM7 architecture. So ARM7 architecture has 16 registers, that is R0 to R15 namely. And all these registers are 32-bit registers, and among that some of the registers are used for special purposes. For example, R15 register is used as a program counter, R15 is used as an LR register, and R13 is used as SP, which is a stack pointer. And we know that some of the registers are banked, meaning which they would be used in different ways during different modes of operations of ARM. And we'll be seeing the details of this in the modes of operations of ARM video. Now coming to the major register over here is R15 register, which is a program counter. This register gives the 32-bit address of the instruction that is to be fetched. So this is the program counter is R15. So it gives the address of the instruction that is to be fetched and places this address in the address bus. The address is put on the address bus, and then the instruction is fetched from the memory through the data bus. Here you can see the data bus is here. Let us assume that there is a memory here. So once the address is put in the address bus, the address goes to the memory, fetches the instruction, and then instruction is put into the data bus. Now coming to whenever an instruction is executed, as we all know that it has to undergo 3 phases. The first phase is known as fetch, and the second is decode, and the third is the execute phase. Now during the fetch phase, what are all the components in the ARM architecture that would be used is given here. So during fetch, we will be using the program counter to get the address of the instruction to be fetched, which is then placed into the address bus. The address bus carries the address to the memory, fetches the instruction from the memory, and then places the instruction into data bus. So all these four play a major component or major role in fetching an instruction from the memory. So if an instruction is fetched from the memory, then it has to be decoded. So for it to be decoded, it moves on to the instruction decoder. And once the instruction decoder decodes the instructions, it generates control signals for execution. The third phase is the execute phase. So for an instruction to be executed, the components that are used in the architecture are the arithmetic and logic unit, which does all the arithmetic and logic operations. It performs 32-bit arithmetic and logic operations. And of course, it has to make use of the data bus to fetch the operand from registers. Please make a note that all the operands for the ALU are obtained only from registers R0 to R15, and no operand is fetched from memory. And of course, we also have a special unit called memory accumulate, which we will be seeing at the later part of the video, and it also makes use of the memory. Now, one of the special functions of ARM7 is the ALU of ARM7 allows triadic operations. What do I mean by triadic operations is, we would have seen an instruction like this, add R0, R1, which means the content of R0 register and R1 register would be added and the result would be stored back in R0. This is a normal execution. But in ARM7, we have triadic operations, which means we can make use of 3 registers for performing addition. It doesn't mean that it will add R0 plus R1 plus R2, but it will add the content of R1 register with R2 register and store the result back in R0 register. So how that happens is, the content from R1 register will come into ALU through A bus. The content from R2 register will come into the ALU through B bus, and both will be added, and the result will go through the result bus and will be stored back in R0. Now, what is the major difference between this and triadic operation is, when you perform a triadic operation, the content in R1 and R2 will remain the same even after addition process takes place. So this is applicable in ARM7 architecture. Now we have a special block here which is known as the sign extend block. Now the purpose of this sign extend block is, we know that an ARM7 processor supports 8-bit data, 16-bit data as well as 32-bit data. So what happens is, but all the registers in the ARM architecture are only 32-bit. So if an 8-bit data comes from the memory, say for example, you fetch a data from the memory and put it into data bus. That data from the memory comes and it has to be put into registers, because ALU operation happens only from registers. So when it comes into the registers, the data size is only 8-bit. So it has to be extended into a 32-bit data before it is loaded into any of the registers. And that process is known as sign extension. Let me say it once again. Sign extension is not equal to extension of zeros, meaning which, when I say sign extension, it doesn't mean that we are just adding that many number of zeros. For example, let me tell you how an 8-bit sign extension is done. Let us say that number plus 5 is represented as 0101. Suppose this has to be extended to 8-bit data. What we do is, this is just a 4-bit data, so we add 4 more zeros in front of it to make it an 8-bit data. This is known as sign extension. but sign extension is not equal to only adding zeros. Suppose in case we need to extend the value of -5. Let us say -5 is always, negative numbers are represented in 2's complement. We have studied this in our digital electronic classes. So this is the -5 representation. And suppose if we have to extend the sign for this -5 into an 8-bit data, and then we cannot substitute zeros, but we'll have to substitute ones. So this is, sign extension is nothing but extending the sign bit value. Suppose if the MSB bit, okay, the sign bit is 0, we extend it with 0, and if the sign bit is 1, we extend it with 1. So let us be very clear about what is the sign extension. It is not substituting zeros. And this feature is possible in ARM7. So you can see here, any data that is loaded from a memory into the registers will have to undergo a sign extension, and then only it is stored into registers. But please make a note, the data that goes from a register to be stored or to be written into a memory need not go through sign extension. That is because they are already stored in a 32-bit register, so there need not be a sign extension for it to be stored back into memory. Now coming to the next important feature of ARM7 is it has got a special register called as barrel shifter. That is, ARM processor has a barrel shifter. Now this is used for pre-shifting operands. That is, before giving them to the ALU. Here this, you have the barrel shifter here, and it is nothing but a combination of logic shifter, which means that it can do multiple shifts in one clock cycle. That is why the name barrel shifter, which means it can do multiple shift in one clock cycle. And whenever you do a left shift, it is same as multiplying by 2, and whenever we do a right shift, it is same as divide by 2. So that is about the barrel shifter. Now coming to the next important feature of the ARM7 architecture is the MAC, which is nothing but the multiply accumulate unit. So this is a special unit to perform multiplication, and let me just explain to you what is the why it is called as multiply accumulate unit. Now let us take an example of how we do multiplication in a paper and a pen. Let us multiply 312 into 23. Now first, when we multiply 3 with 2 you get 6, 3 with 1 we get 3, and 3 with 3 you get 9. So this is the intermediate result. And similarly, when you multiply 2, you get 2 with 2 is 4, 2 with 1 is 2, and 2 with 3 is 6. So 624 is the second intermediate result. But what do we do here when we do the multiplication in a processor is, we cannot store these intermediate results and then retrieve them back and then add them as we do in a paper and a pen. But we are only bothered about the final result that we get, which is 7176, which is equal to 312 into 23. So what this multiply and accumulate does is, it takes the two values, that is 312 from A bus, the second value 23 from B bus, it multiplies. And these intermediate results are taken and stored back into ALU. And next time, when it multiplies, again it takes A value, B value, multiplies, and then stores the second intermediate result into ALU. And finally, when it does the final addition, it takes the intermediate results from the ALU, adds it, and gives the final result. So these two values, 936 and 624, which are intermediate results, are stored into ALU, which is then got back into this MAC, added, and the final result is stored back into the destination register. So this is one of the special features of ARM7 architecture, that is, it has got a multiply accumulate unit. Now coming to the different data types that are supported by ARM7 architecture. ARM7 supports three types of data. First, it supports 8-bit data. So there is no special conditions required to store an 8-bit data. It can occupy any location in the memory address. It can be stored anywhere. The second type of data that is supported by ARM7 is 16-bit. So it must be a 16-bit aligned data. That means it must be stored in memory addresses that begins at even addresses. For example, 0, 2, 4, and so on. The third type of data that is supported by ARM7 is Word, which is a 32-bit data, and this must be stored only in 32-bit aligned spaces, that is all the addresses that are multiples of 4. For example, 0, 4, 8, and so on. In a nutshell, to give the applications, it is one of the processors that are used in recent days, and it has got a lot of applications. It is used in personal digital assistants, which is PDAs. It is used in many cell phones, pagers, automotive, modems, and personal audio products. The reason why it has been used in many applications is it is specially made for ASIC designs and ASSP integrations. It supports thumb instructions, which enables it to perform 32-bit performance at just a 16-bit or even 8-bit cost. Okay, and it gives a very increased code density. It has got a high performance, which allows system designers to integrate more into at a lesser price and at a very less power consumption, which is the major advantage of using ARM7 in many of the applications. So that is ARM7 for you. Hope you have understood the architecture and the data flow path of ARM7. Thank you very much.